Greetings, everybody. In this video, we're going to talk about confidence intervals. This is actually going to be one of two videos. We're going to get started on it in this one and then finish it up in the next one. And the idea of a confidence interval is a way of estimating a population parameter. A parameter could be something like a mean or a proportion. We're actually going to be focusing on population means. The idea for how this works for proportion is similar, but it's almost identical. But just for the sake of simplicity, we're going to focus on the mean here. Okay. So here's our agenda. We're going to talk about how to capture the population parameter. How do you make your first estimate at what the population mean might be? Secondly, we're going to talk about how to construct that confidence interval. And that's going to basically be it for this video. In the next video, we're going to talk about how to change the confidence level, look at 90 and 99% confidence intervals. And then we're going to talk about how we can interpret these intervals. Okay, so let's just talk about how to make this first estimate. How do we estimate our population parameter? In this case, think of a mean or something like that. It's a lot like fishing in a murky lake with a spear. You can throw the spear where you see the fish, but unless you're a very good spear fisherman, you're probably going to miss. A much better bet is to use a net. And that's the idea of confidence intervals. They are like nets. We realize that we're probably not going to get the fish on our first stab with the spear, so we're better off being a little bit sloppier in some ways and using a net. So here's an example. Two newspapers used data from a recent poll to report on the percentage of people who smoke. Which paper do you trust more? Paper A reports that 13.2% of people are smokers. Paper B states that with 95% confidence, the percentage of smokers is 13 plus or minus 4%, and you can't read that. There you are, plus or minus 4%. So which one do you trust more? Well, we don't know exactly for sure which paper's right. I mean, it could be that paper A is right. However, it seems more precise, but with this level of precision, I would bet they're probably wrong. I mean, what are the odds that they, from that one poll, were able to accurately measure the actual population percentage? What are the odds? Not very good, I think. But look what paper B did. Paper B gave an interval of answers, right? They said the actual percentage is anywhere between 9% and 17%. I'm just adding or subtracting 4% from 13. So they admit the possibility of error, which of course is going to be unavoidable when you take a sample. And they back up their statement with a level of confidence. They say they're only 95% confidence. So assuming they use correct methods, I would say that paper's B approach sounds better. They may not be as accurate, but they're more likely to be right. All right, so what are we doing when we're trying to spear this fish or trying to estimate the population mean? We're trying to find that population parameter, and we're going to do it with a point estimate. The point estimate is where we aim the spear or where we aim the net. All right, it's that one guess that we're going to make. And we're hoping that that's approximately right, but we realize that it's probably not. So that's our best guess at what we want to know. Okay? The error, which we are probably going to have, is the difference between the point estimate and the actual parameter. All right, so my sample mean is probably not going to be exactly the same as the population mean. The difference between those two values is the error. So here's an example again. A poll suggests the US president's approval rating is 45%. 45% is the point estimate because it came from the poll. It came from a sample. And that's an estimate for what we might guess the actual population's approval rating of the president might be. Now, what is the actual population's approval rating? Well, that's the population parameter. That's the actual percentage. Do we know what that is? No. We're just making a guess with our point estimate from our sample. Okay, so let's get to these confidence intervals. We have the central limit theorem. Okay, and when the hypotheses of the central limit theorem are satisfied, the theorem tells us that point estimates, in this case sample means, are going to follow a normal distribution. That's the great thing about the central limit theorem. It tells us how the sample means are distributed. Okay, and here's just a summary of that central limit theorem here. Now, what are the hypotheses of the central limit theorem? Well, either the sample size needs to be sufficiently large, so either we need a sample size of 30 or more, or the original distribution, we need to know that it's normal. And this is the notation for saying that X is normally distributed. So if one of those two things is true, the sample size is big enough, or the original distribution is normal, then the central limit theorem tells us that the sample means will be approximately normally distributed. And so then you ask, well, what's the mean and the standard deviation of that distribution? Well, the central limit theorem tells us that too. It says that the mean of the sample means is the mean of the original distribution, the mean of the distribution where the values came from that we used to compute the sample, the sample mean. What's the standard deviation of the sample means? Well, it's the standard deviation of the original distribution divided by the square root of the sample size. And by the way, this is also called the standard error, and often abbreviated SE. And I'm going to refer to this as the standard error throughout the rest of this video. All right, so it is the standard deviation of the sample means. Okay, but we're going to just call it SE, standard error. Okay, so what we see here is just a picture describing what the central limit theorem says. It says the sample means are approximately normal, so here I've drawn that picture. So we know the X bar is going to follow a distribution that looks like this. The question is, how big of a net do we need to ensure that point estimates are going to capture the population mean 95% of the time? How big of a net do I need so that I know that when I throw the net down, I'm going to catch a fish 95% of the time? So to get an idea about this, I have an example ready. Okay, so here I have the distribution that the sample means follow. A picture of the normal distribution here. And what I've done is I've found where the middle 95% of that distribution lies. It falls between this value and this value. All right. Now the values that you see on this axis, these are z-scores. All right. So these are numbers of standard deviations or numbers of standard errors. All right. And if you look at the value, it's just short of -2 here. It's just short of +2 here. The exact value is 1.96. So what this is saying is that if I move 1.96 standard errors to the right, I will get to here. And if I move 1.96 standard errors to the left, I get to here. Okay? So that's what I need to shade in this region. Okay. So what I'm going to do is I'm going to go ahead and consider a bunch of sample means. So suppose I go ahead and take a sample and I get sample means. Some of them will land here, some of them will land here. If I take different samples, I'm going to get means in different places, right? They're going to be scattered about. Some of them will land way out here. Some of them will land way over here, right? The bulk of them are going to land in here because that's the bump of the distribution saying that's where most of them lie, okay? Now what I'm after is I'm after knowing what the true population mean is. Where's that in that picture? That's right in the center, right? That's right here. This is the true population mean. That's my fish. That's what I want to catch, okay? But when I go out and take a sample, I'm going to get a value on one of these dots. I'm going to get something else, okay? So what I'm going to do is I'm going to build a net. Now, how big of a net am I going to build? Well, what I'm going to do is I'm going to use an interval this large. Okay, so I'm going to build an interval that large centered about my x bar. And I've done that. Here we go. So I have an x bar, and I've gone 1.96 standard errors to the right and 1.96 standard errors to the left. You'll notice that lines exactly up with that distance that we see there. So if I had taken a sample mean, and suppose I got this one right here. That was my sample mean. Okay, I missed the true mean, but I don't know that because I don't know what the true mean is. But what I'm going to do is I'm going to build around that sample mean, I'm going to build this interval. Okay? So what I'm now asking is, was that interval sufficiently large so that I caught the true mean? Was my net big enough? Well, I can see here that, yep, it is. The true mean is in my net. So it worked for that sample mean. What if my sample mean was this one over here? Is this net big enough? Well, if I go over here and look at it, did I catch the mean? Yep, I got it. So if I said the real mean was between here and here, I'd be right. So for all these sample means in here, it seems to be working. If I center this at these values, I'm catching the true mean. But what if I take a sample mean out here? What if that was my sample mean? That's possible that I could get one. Not likely, but it's possible. Did I catch the fish? I did not. Notice it's a little bit to the left of my net. I missed. Or what if my sample mean was over here? Did I catch the fish? I did not. I missed. So the question is, what percentage of my sample means are going to catch the fish? Well, as long as my sample mean is in here, I'm going to catch the fish, as long as it's in this shaded region, right? That's what I need to catch the fish. What percentage of my sample means are in there? There's 95%, right? That's what it means to be a 95% confidence interval. It means that 95% of the time, the interval we construct is going to catch the true mean, okay? And so we need our interval to be this big. And so we need our interval to be 1.96 times the standard error. And we're going to add and subtract that from our sample mean, and that's how we go. If I subtract it, I go to here. If I add it, I go to here. That's what gets me my interval. Okay, so that's how we do it. That's how we get our confidence interval. So that's the answer. In a normal distribution, 95% of the data is within 1.96 standard deviations of the mean. So our net should extend 1.96 standard errors to the right and to the left of our point estimate. So that is the formula for the 95% confidence interval. And if you look at what's happening, I don't think we need this picture. I think what I demonstrated was pretty good. So here's our formula for how we're going to do this. I've just summarized it in this blue box, okay? And let's do an example, okay? So it says exam scores. Suppose scores on exams in statistics at a college are normally distributed with an unknown population mean and a population standard deviation of 9 points. A random sample of 40 scores is taken and gives a sample mean of 74. Find a 95% confidence interval estimate for the population mean exam score. We want to find out what is that population mean. Well, let's write down some of the things we do know here. Okay, we were told that we don't know what mu is. That's what we want to find, all right? We want to find mu, okay? We want to estimate it. What do we know? We know the standard deviation. We're told that the standard deviation is 9. We took a sample of size 40, so we know n is equal to 40. And we got a sample mean of 74. Okay? So we have some distribution, right? And our sample mean is somewhere in here. It's probably not in the center, right? Our sample mean might be over here. That's our 74. Maybe it's to the left, maybe it's to the right. I don't know. But we want to try to create a net big enough so that it captures the true mean, which would conceivably be over here. According to this picture, it would be right in the center, right? So we want to try to capture that mu. So how do we get that confidence interval? Where I'm going to go 1.96 standard deviations to the right, that's going to get me this value, and 1.96 standard errors to the left, that's going to give me that one. Okay? How do I get the standard error? Well, the standard error, remember, according to the central limit theorem, is the sigma divided by the square root of n. So that is 9 divided by the square root of 40. That is approximately 1.42. Let's go to 4 decimal places just to be safe. 1.4234. That's 30. Okay. What's 1.96 times the standard error? What do I get when I do that? Well, I get 2.79 approximately. Okay, that is called my margin of error. That's how big my net's going to be. It's the radius of the net, so it's half the size. Okay. So to get the confidence interval, what I'm going to do is I'm going to add and subtract this from the sample mean. So if I subtract this value from the sample mean, I get 71 point, let's just round to 1 decimal place, 71.2. And if I add it to the sample mean, I get 76.8 approximately. And that's my confidence interval. My confidence interval is the interval from this value to this value. And so how do we describe this in words? Well, we say we're 95% confident that the true population mean exam score is between these two values. And there we go. That is our confidence interval. Okay, and that is it for this video. We're going to pick up on the next video and talk about confidence intervals of different sizes and ways to interpret these a little bit more carefully than we did in this video. Okay, so hopefully I'll see you there.